Yeah, let's start the demonstration of this deadbeat controller with my WinDev C# tool. First, after start, I simulate my hardware with my hardware simulator, switch my process to our given process K3, 0.5 seconds, 100 milliseconds. This is okay. Here you see the A is the well-known value, B1 is 0.54. We have calculated manually by hand, so this is okay. First, here I want to have the ideal algorithm, and the hardware simulator, my simulation depends on which type of algorithm the controller works. Of course, if you have ADC cards connected, then this is independent of real or ideal algorithm. In the controller design box, I now do the same. I design for the same process, so I type in the same values again. 100 milliseconds, click on controller design, first ideal mode, controller design, and here you see that the controller design offers these 5 classical controllers, PID versions. For a PI, of course, this for a PT1 process, PIDT1 is senseless. Yeah, a PI can be very fast. So here you can see the deadbeat first version with our both Q0, Q1, P1 here. This, of course, this must also be 1, but in this table I have to type in a value. Here, this is my P1, this is Q1, Q0. If you compare with our nodes, you will see exactly the same values, and the second version of deadbeat is also offered. Here you see the R value is not changeable. I have selected that R, which makes the best behavior. That means the smallest Qs for smallest amplitudes in both cases, for the first and second step. And you see here Q0 is this, Q1 is 0, Q2 is negative 0.677, P1 is this, P2 is this. So I now say OK and copy. All controllers now available in the my controller box, Adaptive Advanced Controllers, and I shift this box into my video window. Have to select now same sampling time. I only want to see 10 points. That is rather enough. I activate this XR button. This is my controller output. Here in this program still called XR. In my new paper I select the letter for the controller output as Y. Okay, doesn't matter. I click to unit step function. Don't forget to click to ideal. If this doesn't fit to your process, this doesn't work. Or you get unstable situations. Let's look what happens with my deadbeat controller. Unit step function, X and XR values are activated. I click on run. So this is the initialization of the controller loop, the control loop. And if I click on this button, we see the reference step response. So I shift this a little bit higher, that you can see all values. The red curve is the controller output value, a little bit larger than 1.8, one step long, then go back to 0.33, and here the blue curve is just not the exponential function here. In this program I calculate this point, I calculate this point, and connect all points just with a straight line curve. Yeah, so you see after one step this control loop is finished. We can do the same now with the real algorithm. I click on real parameters, but of course in my hardware simulator I also have to select the real algorithm. Here this is copied, you see. But if this has not the same setting, then in the controller I can show you what happens in this situation. Yeah, I just click on run. Now you have to wait until this is 0. I can help. The hardware simulator, of course, has the possibility that I force all internal values to 0, like 0 initial conditions, and click on this, and then you see the 2 new curves. This is the black curve is now the new controller output, 1 step delayed. The green curve is the output of the process, and just you see all signals are the same, but just delayed with 1 step. Okay, I delete the last both curves. Here's the delete one curve button, because now I want to show you the deadbeat μ+1 version. For this purpose I go back to ideal algorithm. Of course in the hardware simulation also ideal, you see this, if I change the controller automatically the hardware is adapted, but there is not a copy from hardware simulator into controller, yeah, then you have to be careful. So if I run this controller now, you will see what happens. First run, init process, start, and now you see the black curve is the new Q0, but now 2 steps long, and here's the switch back to 0.33, and the green curve now is the resulting process output. Takes 1 step longer, but now the amplitude is much smaller. So the actuator here has only to amplify a 1 volt value. Here has the actuator amplify a 1.8 volt value, so 80% larger. And you have to decide if you want to have this or that design. Okay. Yeah, the next step is a second order system, to show you that a second order system can have a second step, needs 2 steps, and the second control output value is strong negative. Okay, I go back to the paper. But before we go to a second order system, just have a quick look on chapter 9.4. You see this is a headline: direct design of a deadbeat controller from FFP without the intermediate step of the step response invariant filter version. Yeah, in 9.3 we have seen that we need to calculate the deadbeat controller. We need the ASMBs of the step response invariant filter function. In 9.4 this is just hidden. Of course internally I have calculated these with the same method, but here just you have to put in the k and the t, and then the both q's can directly be calculated with these equations. Yeah, that is the result is of course the same, but here you have no a's and b's. Same as here for a 2PT1 process. If k, t1 and t2 is given, here you can easily calculate the 3 q's and the both p's, because here p1 plus p2 is 1. You should not forget that p1 is then 1 minus p2. The same third typical process is an IT1 process. Here you can find, if k and t of an IT1 is given, you can find the 3 q's and the p1 and p2 equations with these equations without the way through the step response invariant filter function, without the A's and B's. So if you use this, the A's and B's are unknown. Sometimes the A's and B's should also be known. One hint more for my paper, you see this is version 3.2. Now in the course you will find version 3.3, because I have seen that in my document here, this old document, the process output now here is a Y and the controller output is an X index R. That's not fitting to other equations in my paper. So normal is that the process output is called X and the controller output is called Y. So I have changed this. So note also in these equations I have changed the letter. Please use the version 3.3, then this is a little bit more consistent as of the using of the letter. Yeah. Okay, so second order system. Let's have a quick look in chapter 9.5. There I have two examples of deadbeat controller loops. You see this is the same PT1 I have used in my previous videos. Here you see the example is executed with the real algorithm. Here you see I have calculated the FFZ with the step response invariant filter version. The result is of course the same. Here I have calculate exactly all the same values. Here you see the only difference to my example is here we have not a unit step, the input, sondern the desired value jumps to 2. So all signals are factor 2 larger. Yeah, the first impulse is not 1.8 but 3.6 and so on. So I think this doesn't matter. And here what I want to show you is the 9.5.2 example. I want to go through with you. That was also an old examination task. The PT2 is given. The K is 2. We have 0.1 and 0.2 values for the time constant, and the sampling time should be 20 milliseconds. And I want to show you the signals after a step response. There is no given value for the desired value. I think then we should calculate a unit step response. Yeah. I think note now I have the version 3.3. If I go back to my equations, you see here I have, for example, in this chapter for the IT1, I have exchanged the XR letter with Y because this fits more to other processes here. In all these equations, I throw out XR and replaced with Y because this fits better to my old versions. If you go here, the same, yeah. The controller is Y divided by XD, and here the process is X over Y. X is the output, Y is the input of the process. So this, I think, hopefully is less confusing. So please use chapter version 3.3 for further. You will see other chapters are unchanged. Okay, yeah, let's go to the paper and look for my pencil. Okay, next example. C doc. I have a deadbeat controller. Then working with an I2PT1 process. Gain 2, 0.1, 0.2 time constant, negative feedback. This is x, this is y, this is xt, this is w. And sampling time is 20 milliseconds. First, we need the step response invariant filter version, which can be written as b1 z to the power of -1 plus b2 z to the power of -2, 1 plus a1 z to the power of -1 plus a2 z to the power of -2. D should be 0, so I want to have just the ideal version, ideal algorithm of algorithm. Okay, the values can be calculated with either a computer program or with the equations here in my paper. Direct equations, now we have to go to 9.1 here, 2pt1, here the a's and the b's can be calculated with these equations on page 63. See page 63, and a1 is and a2 is. I take the values and put this is 0.01811, and b2 small 0.01638, a1 is a negative 1.724. 4 significant digits are okay. I think this should be rounded to 9, the last letter, then we are correct. And a2 is 0.7408. Okay, if this is true, then you can write the algorithm in the following way. The output x, the response of my outputs of my controller xn, then can be written as 1.724 xn minus 1 minus 0.7408 times xn minus 2 plus b1 y, the input one step before. Here we have a z to the power of -1. Ja, jetzt habe ich das nicht kopiert, sorry. I want to have the numbers here. Plus 0.01811 y of n minus 1 plus 0.01639 times y of n minus 2. Yeah, because the process is x is the output and y is the input. Okay, now the BC equations. Q0 is now 1 divided by B1 plus B2, the sum of the B's, is ... result comes. Yeah, because the B's are rather small, this value is rather large. The smaller the B's, the larger the Q. That's just a normal situation. So we get now 28.99, 4 digits. Then we have a Q1, which is Q0 times A1, gives negative 49.99 0.95. Q2 is Q0 times A2, calculated as 21 times 47. P1 is Q0 times B1, ends up in 0.5250, and P2 is Q0 B2 is 0.4750. Before we start, so this values with 4 significant digits coming from my paper, or you can just take WinDF C# to calculate these numbers. I think the equations are given. Placing the values into these equations is not a really big problem, just a time-consuming way, but easy to do. We now want to calculate the DC gain of the deadbeat controller, because this could be very interesting, because the DC gain gives me some information what the control loop does with disturbances and control errors in after large times. The DC gain. PI controller has a DC gain of infinity. How large is the DC gain of this deadbeat controller? Let's look. The control algorithm, where I have to replace the Z with 1. Now that the DC gain can be written as Q0 28.99 minus 49.95. Z to the power of minus 1 is 1 plus 21.47 divided by 1 minus P1 0.5250 minus 0.4750 gives, in the denominator you see this sum of both p's. If you add them, it's exactly 1. 1 minus 1 is 0, so we divide by 0, and here in the numerator we get the value. Okay, with my calculator I get 0.51. This is the 3rd digit here in my numbers. I have calculated with 4 digits, so this is not an error, that is just not 0. So we can say, okay, the limit value is infinity, so we can say this controller has 0 control error. This controller delivers or works with, gets 0 control error, like PID. So we can be sure that if I have disturbances, this controller can compensate this disturbance completely. Okay, now I want to show you how to calculate these values. If you see in my workbook, then you can exactly look for the same numbers, but you should know the way how to come to the solution. I want to work with a unit step response. So W is running on 1. Here I want to have the output of the process values. Then here the control difference values. And finally here the controller output values. The first line is easy. We know, because of the process function has no B0, independent what the controller here is doing, this stays at 0 in the first moment. So we can say at once this must be a 0. So this becomes a 1 because it's a control difference w minus x. Yeah, don't forget, control difference is just the subtraction of both values. And yn can be calculated. Oh, I have not written this yn value. I should do this in short form. Yn is 0.5250 times yn minus 1 plus 0.4750 times yn minus 2 plus 28.99 times control difference undelayed minus 49.95 xd one step before plus 21.47 times xd two steps before. This is a way to calculate, and in the first moment, if n is 0, all negative arguments are initialized to 0. This 0, this 0, this is a 1. You see the first impulse amplitude is always the Q0 value, 28.99. So 1 volt input delivers nearly 30 volt output. That's a gain of 29. And that means this is a very large impulse, which normally, if this is a really 1 volt step, then this is cut by the limiter of my DIC. Independent of this, the next step is I need x1. I expect 2 steps. This is a DLP controller with a second order system, so I need 2 steps. So in the first step, this could not be a 1. Let's calculate this result with n is 1 is 1. X1 is x0 is 0, x minus 1 is also 0, so these both values are 0. Here we have x1. Here this is y0 is our 28.99 value, so we can calculate 0.01811 times 28.99 plus 0, because this is still 0. So this is just a product of these both numbers, and the result is a value which is 0.5250. So x is 0.5250. xd is the difference to 1 is 0.4750. And now the y1 value is interesting. Now I just make this in small steps. y1 is now 0.525 times y0 is our 28.99. This value is still 0, so I have to use now plus 28.99 times xd. 1 is 0.475 minus 49.95 times xd one step before, and this is our 1. So the result now is, you see, this plus this is 1 times 29 minus 49 gives nearly minus 30. That is what I have told you. 50 minus 30 is 20, and you see this becomes a value negative 20.96. So we start with a large positive value, and the second impulse is a large negative value, which means cooling in a temperature control system, which means braking in a speed control system. Depending on the hardware, it's sometimes it's not possible to realize negative controller output values with the given actuator. I want to make it now very fast to come to the next video with a simulation, with a demonstration, because if you continue now these values, see in my paper, try it for your own. That was an old examination task, and could be that this you can find in your examination a similar task. Finally, this becomes a 1, and this becomes then a 0, and here we get then an 0.5 if you calculate all values with good accuracy. This is the value 0.5, the value which is necessary to hold the output at 1 if the gain of the process is 2. We need here an 0.5 times 2 gives here a 1 for stable situations. Yeah, so this is the situation. We have a controller output value which looks like this. Yeah, controller output in blue is a very large impulse here, a very large negative impulse here, and then a very small value here. So this is 28.99, this is negative 20.96, and this ends in 0.5. Yeah, so this gives in red your output signal. We can say, okay, that is here too. Yeah. After 2 steps you reach the 1. Settling time is 2 times t sampling time. Okay, so I think I stop here, and the next video will show you exactly this behavior with my simulator.